Atomic Physics, Lecture 4, Solution of the Schrödinger equation for a hydrogen-like atom, Principal Quantum Number. Paragraph 1, Parameters that determine the state of the electron. As a result of solving the Schrödinger equation, various wave functions are obtained, differing in the average distance from the nucleus and the angular momentum of the electron. Consequently, an atomic electron can be at different distances from the nucleus and have different angular momentum values. Let's note that the state of the electron, in addition to the distance from the nucleus and angular momentum, also depends on the direction of the electron's spin. However, the dependence on spin is not taken into account in the Schrödinger equation, and therefore it is introduced additionally. Momentum, being a vector, has magnitude and direction. Consequently, each wave function resulting from solving the Schrödinger equation is determined by three parameters: the distance from the nucleus, the magnitude of the angular momentum, and the direction of the angular momentum. Thus, the state of an electron in an atom depends on the average distance from the nucleus and on the magnitude and direction of the angular momentum, plus the direction of the spin, which is not yet taken into account. Consequently, its energy and the type of orbital it occupies depends on these quantities. The energy and type of orbital are found using the electron wave function. As it turns out, while the wave function depends on the average distance and angular momentum, the energy of the electron depends only on the distance from the nucleus. That is, it does not depend on the angular momentum of the electron. The type of orbital depends on both the distance from the nucleus and the angular momentum. Paragraph 2. Discreteness of permissible distances and moments of impulse. From the form of the wave functions obtained as a result of solving the Schrödinger equation, it follows that not any value of the distance from the nucleus and not any angular momentum of the electron corresponds to a wave function. Consequently, the electron may not be at any distance from the nucleus and not have any angular momentum, not any direction, and not any orientation. An electron can only have certain discrete values of these quantities. These discrete values can be numbered. The numbers that number the permissible distances from the nucleus are called the principal quantum number. That is, different distances correspond to different values of the principal quantum number. The numbers that number the permissible values of the orbital momentum are called the orbital quantum number. That is, different values of the orbital momentum correspond to different values of the orbital quantum number. The numbers that number the permissible directions of the orbital momentum are called the magnetic quantum number. That is, different directions of the orbital momentum correspond to different values of the magnetic quantum number. Paragraph 3. Numbering of wave functions, energies, and orbitals. Since each wave function has its own distance, its own angular momentum, and its own direction of the angular momentum, this means that each wave function has its own principal, its own orbital, and its own magnetic quantum number. That is, each wave function corresponds to three values of these numbers. This means that the set of possible wave functions is numbered using three quantum numbers. That is, using the principal, orbital, and magnetic quantum numbers. That is, each state of an electron in an atom is uniquely determined by the three indicated quantum numbers. Each energy value corresponds to its own distance value and therefore its own number of the principal quantum number. Thus, the possible energy values also form a discrete set. That is, an electron cannot have any energy but only one of the permissible ones. The permissible energy values are numbered using the principal quantum number. In this case, the state with minimal energy is the ground state, and the rest are excited. Each orbital has its own principal, orbital, and magnetic quantum numbers. This means that the orbitals are numbered by 3 quantum numbers. Paragraph 4. Degeneracy of energy levels. As can be seen, the same energy value corresponds to several different wave functions that have the same principal quantum number but different orbitals and magnetic quantum numbers. That is, different magnitudes and directions of the orbital momentum. That is, being in several different states, in several different orbitals, an electron can have the same energy. Therefore, they say that the energy levels of the electron in a hydrogen-like atom in the Schrödinger approximation are degenerate. Let us now consider what each of the quantum numbers means. Paragraph 5. Principal quantum number. The principal quantum number is associated with the main parameter characterizing the state of the nucleus plus electron system, with the difference of the electron from the nucleus. The principal quantum number numbers the set of distances at which an electron can be located from the nucleus. Note that since the orbital is a volumetric region, being in it the electron is simultaneously at different distances from the nucleus. Therefore, the distance between the nucleus and the electron is understood as a certain average distance. By determining the average distance of an electron from the nucleus, the principal quantum number thereby determines the size of the electron orbital. The further the electron is from the nucleus, the larger the size of the region in which it can be located. That is, the larger the size of the orbital. Thus, the principal quantum number numbers the orbitals in order of increasing size and distance from the nucleus. Moreover, at each of the allowed distances, there may be several different orbitals differing in other quantum numbers. That is, several orbitals correspond to the same principal quantum number. In addition, the principal number determines the energy of the electron. It numbers the electronic energy levels in order of increasing energy. The principal quantum number can take the values 1, 2, 3, 4, etc. The distance of any orbital from the nucleus is directly proportional to the square of its principal quantum number. This means that it is equal to the square of the principal quantum number multiplied by the distance from the nucleus of the first or closest orbital. In the special case of the hydrogen atom, this distance at which the first nearest orbital is located is approximately a half angstrom in order of magnitude and is called the first Bohr radius. It is obvious that as you move away from the nucleus, the distance between orbitals with neighboring values of the principal quantum number increases. An orbital with a principal quantum number of 1 is closest to the nucleus and corresponds to the minimum energy of the electron. Thereby, it corresponds to the ground state of the atom. All other orbitals correspond to excited states. Note that the distance of the orbital from the nucleus and its size depend not only on the principal quantum number, but also on the charge of the nucleus, or on its effective charge in the case of screening of the bare charge by electrons close to the nucleus. Both the distances from the nucleus and the size of the orbitals decrease with increasing nuclear charge in inverse proportion to the square of the charge. Paragraph 6. Kinetic, potential, and total energy of the electron. The total energy of an atomic electron is the sum of its kinetic and potential energies. The rest energy of the electron is not taken into account since it is taken as the zero energy reference point. Kinetic energy is positive and potential energy is negative. In an atom, the potential energy of an electron is greater in absolute value than the kinetic energy, so the total energy is less than zero. The absolute value of the total energy of an electron is what is called binding energy. This is the amount of energy that an electron lacks to overcome the attraction of the nucleus. In other words, this is the minimum energy that must be imparted to an electron in order to tear it away from the atom. Obviously, the greater the modulus of the total energy of an atomic electron, the greater its binding energy and the more firmly it is bound to the nucleus. Paragraph 7. Dependence of energy on the principal quantum number. In the orbital closest to the nucleus, with principal quantum number 1, the total energy of the electron is minimal. Moreover, this energy is maximum in absolute value, which corresponds to the strongest connection between the electron and the nucleus. The farther the orbital is from the nucleus, the lower the kinetic energy of the electron and the greater its potential energy, which corresponds to a weakening of the electron's bond with the nucleus since potential energy is negative. The total energy of the electron decreases in absolute value as it moves away from the nucleus, but increases in value. In this case, both the kinetic and potential energies of the electron in each orbital are inversely proportional to the square of the principal quantum number characterizing this orbital. Therefore, the total energy is also inversely proportional to the principal quantum number. This means that it is equal to the energy of the electron in the first orbital divided by the square of the principal quantum number. Thus, as we move away from the nucleus, the energy distance between orbitals with neighboring values of the principal quantum number, that is, the energy difference between these orbitals, decreases, while the usual physics distance increases as mentioned above. Note that the electron energy depends not only on the principal quantum number, but also on the charge of the nucleus. For the same principal quantum number, the greater the nuclear charge, the greater the energy will be. The energy is proportional to the square of the nuclear charge. Paragraph 8. Speed and wavelength of the electron. In addition to the energy of the electron, the principal quantum number determines such quantities uniquely related to energy as the speed of the electron and the length of its de Broglie wave. Thus, the speed of an electron being proportional to the square root of its kinetic energy turns out to be inversely proportional to the principal quantum number. This means that the speed of the electron is maximum in the orbital closest to the nucleus and decreases as it moves away from the nucleus. Calculations show that in the orbital closest to the nucleus, the speed of the electron is approximately 2,000 kilometers per second. This is about 1% of the speed of light. It follows that the electron in the hydrogen atom can be considered non-relativistic with fairly good accuracy. For atoms with a nuclear charge greater than 1, the corresponding electron speed will be greater. The magnitude of the speed is directly proportional to the nuclear charge. Consequently, for such atoms, relativistic effects become more noticeable. The length of the de Broglie wave of the electron is inversely proportional to the speed and therefore to the principal quantum number. Consequently, the electron wavelength increases with distance from the nucleus. In this case, the wavelength will be shorter the greater the nuclear charge.